Hello everybody. Today I'll be talking about my image processing and computer vision project on shape from shading. It is one research area in image processing and computer vision that is commonly worked on. This topic is very much in demand nowadays, which finds applications in a number of fields, for example, in medical sciences and security systems. In this project, two inputs were fed and then the simulation was carried out to obtain a three-dimensional shape. One of the inputs was a regular two-dimensional shading image obtained from a spherical structure, and the second input was another two-dimensional shading image obtained from a non-regular human picture as the object. Now to begin with, here we have a brief outline of the project. First, we start with the basic concept of shape and shading. Then over to the considerations for the project, the assumptions kept in mind while carrying out the project, the implementation of the project, followed by the simulation results using the two input types, and finally we have the conclusion, references and the acknowledgement. To start the project, let us begin with the concept of shape from shading. The first thing we need to study is that of the shading images. Shading images are not merely the shadows of the objects, but that they are the grayscale images of the objects. They are the images that vary in grayscale in density. These images are two-dimensional in nature and they are used for the reconstruction of the three-dimensional shape of the object. Now for the determination of the three-dimensional shape from the shading images, the knowledge of the scene of radiance is required. The scene of radiance can be evaluated by three factors. First is by the light falling on the object. Second is by the fraction of the incident light that is reflected from the surface of the object. This is also known as albedo. Finally, the third factor is the geometry of the surface, which again can be obtained from the shape of the object and the viewpoint. All these information are required to correctly obtain the three-dimensional shape from the two-dimensional shading images of the objects. Now moving over to the considerations. In this project, it has been considered that there is a three-dimensional object which is illuminated by a light source, illuminating the object and producing its two-dimensional shading image on the image plane. In this figure, the first rectangular plane is the image plane. The source of light S, which is a function of x, y and z, illuminates the object. Now the reconstruction of the three-dimensional shape from the two-dimensional shading image requires various information that is obtained from the image irradiance equation given on the slide, and it is equal to the capital E of x and y equal to the capital R of PQ, where P and Q are themselves functions of x and y. E of x and y is the image irradiance function, R is the function of P and Q, and it is the radiance function. P and Q are themselves the partial derivatives of the surface of the object in the directions x and y respectively. So the image irradiance equation gives us the information that is quite essential for the reconstruction of the three-dimensional shape from its corresponding two-dimensional shading images. Now coming to the assumptions that have been taken into account for the project. First, we have the orthographic projection. It has been assumed that the object is located at a position which is far away from the viewing plane. Those light rays that are perpendicular to the plane of view are the only ones incident on the object. As a result of this, the xy coordinates of the image are similar or in fact equal to that of the coordinates of the object. Thus, the irradiance equation can be modified as the one given on the slide. That is, E of small xy equals to the radiance function R of PQ, where P and Q are the partial derivatives of the object surface in the direction x and y respectively. It is also assumed that the surface of the object is a Lambertian and a matte surface. Lambertian surface means that the reflected energy coming out of the object has uniform value in all directions. The reflected energy from the object is only dependent on the cosine of the angle of incidence. Matte surface means that there are no shining points on the surface of the object. The third assumption is that the light source is located far away from the object. And finally, the intensity and the position of the light source are known to the person doing the project. Now moving over to the implementation of the project. Taking into account the considerations as well as the assumptions discussed previously, the image irradiance equation can be represented as the one indicated with equation 1 in the slide. That is, capital E of P and Q, where E has now become a function of P and Q, where P and Q are the partial derivatives of the surface of the object in the directions x and y respectively, is equal to the double integration of E of small xy minus r of pq whole square plus lambda of the sum of px square, py square, qx square and qy square. Here, the first term, that is E of x and y minus r of p and q whole square, is the image data befitting term, which is minimum when the image irradiance is equivalent to the image of the object approaching the shading image. The second term in this equation is the smoothness term, where lambda adds weightage to the smoothness. Higher the value of lambda, more will be the weightage added to the smoothness of the surface, and vice versa. Hence, the value of lambda is significant to judge the smoothness of the image for simulation. Now, taking E of P and Q as the cost function, we need to find the solution, which is the reconstruction of the three-dimensional shape from the two-dimensional shading images. Now, minimizing the cost function is a way to find out our solution. The image irradiance equation has been reduced to the function of P and Q. Then we can use the Euler-Lagrange function to obtain the desired results. The Euler-Lagrange functions in P and Q are the ones given by equations 2 and 3, and they are used to minimize the function of image irradiance equation, thereby minimizing the cost function to get the solution. Also, in this project, a 3x3 kernel depicting the discrete equivalent Laplacian is used for further simplification. Now coming to the simulation. The simulation is carried out for two objects as inputs. One object being a regular spherical structure and the other object is somewhat non-regular object of a human picture. The first object produces a regular circular two-dimensional shading image, whereas the second object produces a somewhat non-regular two-dimensional shading image. In the first simulation, the input is a two-dimensional shading image and it can be clearly seen that the grayscale is varying at different points. After running the simulation, we get the P and Q parameters. The information obtained from the P and Q parameters help us in the reconstruction of the 3D image. Then we get the F and G parameters after running the simulation, and the information from these parameters are also obtained. These are shown on the slide. So after obtaining the information from the P and Q parameters and the F and G parameters, the three-dimensional reconstructions from the two-dimensional shading images are done. The first figure under shape reconstruction is the three-dimensional image obtained from the information from the F and G parameters, and the second figure under shape reconstruction is the three-dimensional image reconstruction from the two-dimensional shading image with information obtained from the P and Q parameters. These two shape reconstruction figures are our project outputs of the spherical input. Moving on to the second simulation, here we have a somewhat non-regular object of a human as input, satisfying all the considerations and assumptions as discussed for the project. This object produces a two-dimensional shading image which varies in grayscale as can be seen. After running the simulation, we obtain the P and Q parameters that can be seen on the slide. The F and G parameters are also obtained for the same. Now from the information obtained from the P and Q parameters and the F and G parameters, the three-dimensional reconstruction is done. The first figure under shape reconstruction is the three-dimensional reconstruction of the 2D shading image from the F and G parameter information, and the second figure under shape reconstruction is the three-dimensional reconstruction from the P and Q parameter information. Now, before we move over to the conclusion, let us discuss about our code or simulation. This is our code basically, and it has been run in MATLAB. Now basically various tools and functions have been used for this purpose. We have demonstrated the second input, that is this picture, as the input to the simulation. The simulation took quite a while. We have already run this simulation so that the outputs can be shown now. So the outputs as obtained, this was the P and Q parameters obtained after running the simulation. Then we have the F and G parameters also obtained after simulation. Then finally, we have the output plot for the 3D reconstruction from the 2D shading image. The first plot is the 3D reconstruction from the FG parameter information, and the second is the 3D reconstruction from the PQ parameter information. In a similar manner, the results for the first input, that is, the spherical structure, were also obtained. I am not showing them again due to lack of time. Now coming over to the conclusion of the project, it was found that the reconstruction from a regular image produced better result than that of the non-regular image. It is quite obvious that the regular images are easier to simulate in the simulation environment. Another thing that was found was that the reconstruction using the information from the F and G parameters gave us a better result than the images obtained from the P and Q parameters. Finally, the shape from shading is a widely used concept and finds a variety of applications in the fields like medical sciences, security systems, archaeology, astronomy, and many more. Here we have a list of references that were consulted during the project. Finally, I would like to thank Professor Dapeng Wu for his guidance and stimulation of interest for the image processing and computer vision course. The concepts grasped are extremely interesting and useful for future industrial applications. Dr. Wu has always encouraged us to be creative with our project. He has supported and helped us with all the difficulties faced during this project execution and finally its completion. Thank you.